So now we look at part C in problem 2-4, where we ask, given that the loss was at least C, what is the probability that the storm was of strength 1? So what is the goal of this part? Well, it says, given that the loss is at least C, so given that the loss is greater than equal to C, what is the probability that the strength of the storm is 1? So I'll just write strength here is equal to 1. So the probability that the strength of the storm is equal to 1, given that the loss is at least C, which means given that the loss is greater than equal to C. We want to find this thing here. Okay, so let's just try to write this up. What's the definition of this? Well, recall that when we were reading chapter 2, there was a formula for conditional distributions and also just for conditional probabilities in general, where we saw that the probability of A given B is equal to the probability of A intersected with B divided by the probability of B. So let's just try to use this formula here. So the probability of strength equals 1, given that the loss is greater than equal to C, is given by the probability that strength of the storm is equal 1, and, so the comma stands for and the loss is greater than C, divided by the probability of the event we condition on, so divided by the probability that X is greater than equal to C. Now this down here is not hard to calculate, right? Because we know the density of X, so hence we can find the probability of X belonging to any set. But this one here, the probability that strength is equal to 1 given and X being greater than equal to C. So the joint probability of the probability of the intersection of these two events. Well, how do we find that? For that, we can try to remember yet another trick from just good old probability theory, which is that the probability of A intersected with B, well, if I take a look at this formula above here and I multiply P of B over here, then I know that the probability of A intersected with B is the probability of A given B multiplied by the probability of B. However, I can also see that, well, there's no reason why I shouldn't use the probability of B given A multiplied by the probability of A, right? Because if I had chosen to take a look at the probability of B given A, then that would be defined as the probability of their intersection divided by the probability of A. And then if I multiplied A over here, the probability of A over here, then I would just get exactly this. So this means that if I'm looking at the probability of the intersection of two events here, I can actually write it as the probability of one event given the other multiplied by the probability of the event that I condition on. So this is equal to the probability of X greater than equal to C given the strength is equal to 1 multiplied by the probability I condition on here, so multiplied by the probability that strength is equal to 1 divided by the probability that X is greater than equal to C. Now this is actually already pretty nice because we know that the probability that the strength is equal to 1 is given by P1, right? So we can kind of put a green circle around this. We know what this is. And we can actually calculate both this and this, which means we'll be able to find the value of this whole thing. So let's just take a look here. What do we want to calculate? There are two extra things we want to calculate. We want to calculate the probability that x is greater than equal to c given the strength is equal to 1. So given that the strength is equal to 1, we know that x is how distributed? Well, given strength equals 1, we know that x is exponentially distributed with parameter lambda 1, right? So we get that the probability of x being greater than equal to c, given that strength is equal to 1, is just the integral from c up to infinity of the density of an exponential distribution with parameter lambda 1. And that was lambda 1 multiplied by e to the minus lambda 1 x dx. And if I integrate this, what I get is just, let's see, what do I get? What I get is e to the minus lambda 1 x, because I will have lambda 1 divided by lambda 1, which cancel out, and I evaluate that in c and infinity respectively. Oh wait, I also have a minus here, yes, because I take minus lambda 1 down. And this will give me 0 minus minus c, 0 for the upper bound, minus e to the minus lambda 1 c. So this probability here is just given by e to the minus lambda 1 c. Now the next probability I can find as well, and that is the probability that x is greater than equal to c that I wanted. So the density of x is given by this thing over here that we had from part A of the exercise. And what I want to do is I want to integrate the density of x over the set whose probability I'm trying to find. So that is c to infinity here. And when I plug in the value of the density, so the expression for the density, it's a sum from 1 to 3 of pi lambda I e to the minus lambda I x dx. And I can interchange the sum and the integral here. So I will have the sum from 1 to 3 over the integral from c to infinity of pi lambda I e to the minus lambda I x dx. And this gives me the sum from 1 to 3, and I can just take pi out of the integral here, and then when I evaluate the integral, I get the antiderivative minus e to the minus lambda I multiplied by x. I have infinity in the upper bound and c in the lower bound, and this will give me a sum from 1 to 3 of pi multiplied by e to the minus lambda ic as such. So now I have both values that I need for my final expression. So I'm going to plug in the e to the minus lambda 1c up here in the numerator, and I'm going to plug this thing in down here in the denominator. So all in all, we can conclude that the probability, so what was it we were actually calculating? It was the probability that given we know the loss is at least C, then the strength is equal to 1. So the probability that the strength is equal to 1, given that the loss is at least C, is equal to the ratio between the probability that x is greater than or equal to c given the strength is 1, so that's e to the minus lambda 1c, and then multiplied by the probability of the strength being equal to 1, which was multiplied by p1, and then divided by the sum of the pi multiplied by e to the lambda minus lambda ic for I going from 1 to 3. So this is the final result in part C, and doesn't seem too crazy. You just take a look at the probability that x will be greater than or equal to c, and then gauge that given that happens, what's the probability that that the strength will be equal to 1. So this was part C. Now in the next videos we will take a look at mixture distributions. So keep watching, because if you read the part on mixture distributions on your own, it might be a bit confusing. So we will try to read that section together.